In this project, we were to find the acceleration of an elevator at 4 various points. I took a 6-pound weight and measured it on a scale that could measure the changing weight continuously. I took the scale and the weight in an elevator and took video of the changing weight during the elevator ride. I repeated the same procedure going down the elevator, and then I repeated the same steps 2 more times to get an accurate measurement. In theory, the object should have increased in weight as the elevator accelerated upwards in the positive direction, and a negative acceleration in the negative direction. It should have decreased in weight when it had a negative acceleration in the positive direction and a positive acceleration in the negative direction. I hypothesized that if the conservation of mass holds true, the mass at the top and the bottom of the elevator should have been the same, but the mass will increase as the elevator accelerates upwards. The data in this table shows the average of the weights of the 3 runs. As you can see in the table, the weight at the top and the bottom of the elevator is the same. The only time that it changes is when the elevator starts to accelerate and decelerate. As you can see in this data table, we determine the masses by taking the weight of the object and then multiplying it by the acceleration of gravity in order to get the mass in newtons, because a newton is a kilogram times meters per second squared. A newton is also a unit of measurement for mass and force. In order to solve for acceleration, we use the mass equals the sum of all forces equals tension minus mass times the acceleration of gravity. We can then just say that mass times acceleration equals tension minus mass times acceleration of gravity. Then we can move and solve for tension by saying mass times acceleration plus mass times acceleration of gravity equals tension. And making it look a little bit nicer, we can say tension equals mass times acceleration plus acceleration of gravity, and then plug all of our numbers in from there. As the elevator begins to move in the positive direction, the acceleration should also be positive so that it will begin to speed up. As it starts to slow down, however, it should have a negative acceleration in the positive direction for that reason. The tension in this equation comes from the mass of the object times the force of gravity, which is 9.8. If you multiply those two out, you get 28.07, which should then be set equal to the mass of the object, which is in kilograms, which is 2.747 kilograms, times the acceleration, which we're solving for, plus the acceleration of gravity, which is 9.8. If you divide these out, you get 10.21 meters per second because we're dividing newtons by kilograms, which then equals acceleration plus 9.8. These are both in meters per second, so we can subtract them, and we get our acceleration to be 0.418 meters per second squared. Now to solve for the acceleration as it slows down and comes to a stop while it's still moving in the positive direction. We again took the mass of the object times the acceleration of gravity to get 25.17 newtons equal to the mass of the object, which again is 2.747, times the acceleration plus 9.8, which is the acceleration of gravity. If you divide these two out, you get 9.16 meters per second squared equals A plus 9.8, which again is in meters per second squared. Now we can subtract these two and we get negative 0.637 meters per second squared as the acceleration for the slowing down of the positive direction. As the elevator begins to move and it goes to the first acceleration should be negative so that the signs of the direction and the magnitude are the same so that the elevator can speed up. However, as it begins to slow down, the sign should be positive for the acceleration so that the magnitude and the direction are opposite, forcing the elevator to slow down. As the elevator begins to slow down, the acceleration would then be positive as it is going in the negative direction. So again, we find the tension by taking the mass in kilograms times the acceleration of gravity, which then multiplies out to be 28.77 newtons, and we set that equal to the mass in kilograms, which is 2.747, times the acceleration plus the acceleration of gravity. If you divide this out, you get 10.473, and then we set that equal to acceleration plus 9.8. These are both in meters per second squared, so we can subtract this off, and our acceleration will then be 0.673 meters per second squared. Based on our calculations, the two positive accelerations were when the elevator just started to move up, which was 0.418 meters per second, and when the elevator was going in the negative direction and slowing down, which was 0.673 meters per second. We also found, based on our calculations, that the elevator had a negative acceleration when it was just moving in the downward direction, in the negative direction, which was negative 0.564 meters per second. We also found that it had a negative acceleration when it was slowing down, going in the positive direction, which was negative 0.637 meters per second. The first acceleration we found was positive, while also moving in the positive direction, and since the magnitude and the direction had the same sign, that means that the object sped up in the elevator. The second acceleration we found was when the elevator was moving in the positive direction, but also slowing down, which means it has a negative acceleration, which we can see right here. That then forces the object to slow down because the magnitude and the direction are opposite signs. Then we found a third acceleration as the elevator started to move down. Just as it started moving, it was moving in the negative direction with a negative acceleration, which means that they have the same sign, so that means the object is speeding up. And finally, we found a fourth acceleration, which was positive, but it was moving in the negative direction, which again, the magnitude and the acceleration were in opposite signs, so that means that the object and the elevator were both slowing down. Each of the magnitudes are different for each of the accelerations because each acceleration needed to work in a different way. Some of them were able to work with gravity, while others needed to work against gravity. The largest acceleration is shown when the elevator is moving down and trying to slow down because the acceleration needs to work against gravity and the direction. The smallest acceleration is seen here when the elevator is moving up and trying to slow down because gravity is able to help the elevator slow down, but it just has to work against the direction. Because there is no acceleration in the middle of the trip, there's a constant velocity and the weight of the object went back to its original weight. Based on my hypothesis, we can see that because of an upwards acceleration, the object's mass increased, and based on a negative acceleration, the object's mass decreased.